All right, welcome back, everybody. This is MTED110, and today we are doing Chapter 11, Lecture 11A. So let's go ahead and get started. I'll pull up the slides. Okay, so Chapter 11 is all about number theory. And like I had said on the module description, you'll notice that this chapter is much more technical than the previous chapters. So just be prepared to handle a little bit more complexity and a little bit more rigor, mathematically speaking. We'll talk about why I moved this chapter up, but it's a pedagogical choice because we cover things in chapter 11 that can be very, very helpful in chapters 6 and 7, which are all about fractions. All right, let's get started. So first, originally number theory was the domain of pure mathematicians only, but it turned out to have extraordinary wide-ranging applications. So there are some mathematicians from the early 1900s who studied number theory and they loved it so much because it just could never possibly have any application to real life, and it was just pure theory, and it was so beautiful for its theory. Turns out that it's extraordinarily applicable and it's got a ton of applications, most notably modern day cryptography. So modern day cryptography is entirely based on number theory, in particular the theory of large prime numbers. And we're going to talk about prime numbers today. I can talk about that more in the collaboration meeting if you want, but long story short, if I give you a gigantic number, like a number that's got, like, I don't know, several billion digits, and I'll just ask you if it's prime. And if you can tell that it's prime or not, then you can decrypt everything on my computer. That's basically the idea. That's how modern day cryptography works. Okay, so the ideas that we discuss, they can be applied to negative integers, but we're going to restrict ourselves to the non-negative integers, otherwise known as the whole numbers in this book. So we're only dealing with stuff 0, 1, 2, 3, 4, 5, and up, right? That's the idea. Fractions also play a part in number theory, but mostly when we're considering the numerator and the denominator separately. Some of these ideas will be familiar from this class or from your previous education, but we're going to introduce a degree of rigor, and that's the idea. Oh, you might notice this is a particularly long set of slides. That's because there are a lot of divisibility tests. So you remember those things, like how do you know if a number is divisible by 2 or 3 or 4 or 5? We're going to get all of those and prove all of those. So it takes a lot of slides to do that. Okay, so first we're gonna focus on these concepts here. And these are definitions that you need to be very comfortable with. So these are definitions that you should memorize, all right? Definitely memorize these. First, recall this from earlier. Each number in a product is called a factor. So for example, 30 has all of these numbers as factors, 1, 2, 3, 5, 6, 10, 15, and 30. And the reason these are all factors of the number 30 is because we can write 30 as multiples of each of these numbers. So 30 is the same as 1 times 30, it's the same as 2 times 15, it's the same as 3 times 10, and it's the same as 5 times 6. So each one of these numbers is a factor of 30, okay? That's what a factor is. Remember, a factor is a number in a product. So some numbers only have 2 factors. Which numbers do you think those are? Wait, let me get my thinker ready here. What numbers do you think only have 2 factors? What do you think? That's right, it's the prime numbers. The prime numbers are the numbers that have only 2 factors. So let's see the definition. A prime number is a natural number that has exactly 2 different factors. And I'll explain that right now, actually. The reason that we say that it has to have 2 different factors is because we want to exclude the number 1. Let me give you some examples of prime numbers, and you'll see what I mean. So here's a list of some. 2, 3, 5, 7, 11, 13, 17. There's a bunch more. There's infinitely many more, in fact. But the thing about these 2 numbers is they are only divisible by themselves and 1. That's the big idea. They're only divisible by themselves and 1. So they only have 2 factors. And we say that there's 2 different factors because we want to exclude the number 1. We don't really want to say that 1 is a prime number, right? Because you could write 1 as 1 times 1, But the truth is that 1 is a very, very special number. It's the unit, it's the real unit, it's what we use to count. And we don't want to classify it as prime because then every theorem that we have about prime numbers, we would have to add a little asterisk and say, except for in the case of the number 1. And rather than say, except for in the case of the number 1 over and over and over again, we just alter the definition a little bit to ensure that it does not include the number 1. So the number 1 is not a prime number. And that's an agreement that we all came to and basically said, let's not call it prime just to make our lives easier. Okay. Now, by contrast, a composite number is a number that has more than 2 factors. So there's lots of composite numbers too, right? How about 4, 6, 9, 10, 12, 14, whole bunch of numbers. Those are all composite numbers because they have more than 2 factors. For example, 4, let's look at 4. 4 you can write as 1 times 4, or you can write it as 2 times 2. So 4 has factors 1, 2, and 4. Oops. That's the set of the factors of 4, 1, 2, and 4. That's more than 2, so it can't be a prime number. It's got to be a composite number. Yeah, so prime numbers have expansive implications and applications, and I think we're going to get to, next. Oh yeah, they're used as a foundation for cryptography. You can look up more of that if you'd like. The Euclid of Alexandria proved that there are an infinite number of prime numbers way, way, way back when, that way. And also that there isn't a largest prime number. So there is no largest prime number. We continue to find more and more primes. And in fact, we still search for larger and larger primes. I should maybe try to update this actually. As of January 2020, the largest prime ever computed is this one. It's the number 2 to the power of 82,589,933 minus 1. Minus 1. That minus 1 is what basically shifts the whole thing down a little bit. So we'll see this in this chapter. But here, this number has definitely got to be even. That's an even number. And if you're an even number, you're not a prime number, unless you're the number 2. The number 2 is the only even prime number. 2 is another very special number. So this thing that I've highlighted here, that thing is an even number, but then we subtract 1 and it makes it an odd number. So you know it's not, it's at least odd. The other wild thing about this is that it has this many digits. This number is 24,862,048 digits long. And you could look it up to see if there's a longer one discovered now, because this is earlier this year. Yeah, just Google it. Just Google largest prime, and it's either this one or they might have just discovered a new one this summer, but I can't remember. Yeah, we still search for larger and larger primes. There's a project called GIMP, or GIMPS, I mean, GIMPS, and it stands for the Great Internet Mersenne Prime Search. Let me see if I can. The Great Internet Mersenne, French name, Prime Search. And you can actually be a part of it if you want, because what this project does is it asks people to farm out their computer processing power when they're not using their computer. So if you've got a desktop computer at home and you register to be part of this project, what they'll do is when they have to grind through a calculation to determine if a new number is prime, it takes a ton of computing power and a ton of time. Like imagine running a project, or like running a process that takes like months. Well, if you have a whole bunch of computers working on the same problem, it doesn't take as many months. And so what they do is they ask interested individuals if they would be all right linking their computer to this project to allow them to use their computer power when you, the individual, are not using your computer at that time. So you can look into that if you're interested. I did something kind of like that when I was a kid, but it was for SETI, which we'll actually talk about in a minute. Hey, speaking of which, I talk about right here. This is that. Oh, there we go. So this is another really, really fascinating application of prime numbers, and it's the 1974 Arecibo message. This is actually a link. So if you click on that on the slides, it'll take you to the Wikipedia page, and we're going to look at that in just a second here. But the idea was this. The 1974 message was a string of 1,679 binary digits, meaning 0 and 1. So it was basically a string of zeros and ones, and there were this many of them, 1,679. Now, the authors of the message included Carl Sagan and Frank Drake, who were two very, very famous astrophysicists. And actually, what I would like all of you to do is to click this link and watch the video called Pale Blue Dot. Pale Blue Dot is a speech, you could say, given by Carl Sagan way back when that just kind of puts life into perspective. Because once you get a larger, more universal view of your own life and reality, it tends to put everything in perspective. And he was a big fan of that, and he has a very, very beautifully worded lecture, or not even a lecture, it's like a 3-minute video to give you some perspective like that. So I really, really encourage you to watch it, and if you want to talk about that, I'll talk about it too. Frank Drake is actually, he's famous for what's called the Drake equation. He's the one that figured out the probability that extraterrestrial life would exist somewhere. Anyway, so if you're interested in astrophysics at all, or some of your students are, you can always point them to these. This is a good jumpstart for young learners. Anyway, back to the message itself. So the idea was this. They figured that if intelligent life received this string of digits, right? So 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, right? They received this, then they would be able to factor the number 1679 as 23 times 73. Now, 23 and 73 are both prime numbers, and we call this number 1679 semi-prime because it's the product of two prime numbers. So it's like it's almost prime, right? It's like one step away from being prime. And what they did was they arranged the bits. Oh, I'm sorry. What they thought was the aliens that received this message would be able to factor the number 1679, and then they would be able to arrange the bits in a rectangular array. Okay, so I want you to just think about that for a minute. Think about that for a minute. Hmm. Hmm. So first of all, there's some questions here, right? So how would the aliens possibly know to factor the number as 23 times 73? Well, because the concepts of prime numbers and composite numbers and factors, they're completely irrespective of numeration system. It doesn't matter what numeration system you have, as long as you know how to count, or I should say discretely count, then you can factor. You can factor, you can find prime numbers, you can find composite numbers. Those things don't rely on a numeration system, they just rely on the numbers themselves, which is just amazing, right? So if aliens are intelligent, they must know how to count. And if they know how to count, then they're aware of the existence of prime numbers. And if they're aware of the existence of prime numbers, then they would know that they can factor this, right? But they can factor it into two prime numbers, but here's the best part. Remember what I said about multiplication in the previous chapters? It can always be represented as an area. It can always be represented as an area, as a product of two dimensions, right? So that's why they wanted to pick a semi-prime number to send this message, because the only way you can factor it is as the whole string itself or as 23 by 73. Those are the only two options you get for how to factor that number. And they would realize, the aliens, that they could factor it and do this. And when they did that, they should see something like this over here. That's what they would see. And so what I'm going to do here is I'm actually going to pull up this Wikipedia page so we can see how amazing this is and how much information is encoded. Let me pull it up right here. Okay, yeah, so here it is. Come back. There we go. So this is the Arecibo message. And the Arecibo is a radio observatory in Puerto Rico. You can read about it here, the Arecibo Radio Telescope. Oh, unfortunately, OBS doesn't pick up my mouse because I'm using a Mac. That's just some like formatting error on Mac's behalf. So unfortunately, I can't exactly point at what I'm pointing at. Maybe if I scroll up or something, I can be like that right there. Anyway, so this right here, this is a demonstration of what it would look like with color added, and that the color is added just so that we can see what's going on. But there's a lot of information here. So what's cool is that this first uh, upper collection, those white dots, those are the numbers 1 through 10. Here we go. So let me zoom in right here. These things right here, this is encoding the numbers 1 through 10 in binary. And if you don't believe me, because you shouldn't, now you know how to count in binary. We talked about counting in binary, and you could interpret this. They've got the breakdown over here. So here's the number 1. What's the number 1? They're going to go 0, 0, 1. What's the number 2? 0, 1, 0, because you've got 1, 2, and 0 ones, right? What's the number 3? 3. It's 0, 1, 1, because you have 1, 2, and then 1, 1 left over, and so on and so on. The very last is just this is, yeah, a least significant digit marker. This is just to let the aliens know to go to the next line, essentially. That's what it is. But yeah, so that's what this is in the message. And then there's more. So these are the DNA elements: hydrogen, carbon, nitrogen, oxygen, and phosphorus. Down here, these other things, these are the nucleotides that make up DNA. And then this is a double helix, this blue thing right here, a double helix, and that just shows that that's the that's the that's what our DNA looks like, right? Here, there's a figure of a human being with the average height and also the population. So back here, this is the population, right? Where'd it go? Where did it go? The element on the right depicts the human population, approximately 4.3 billion back in 1974. You might be interested to know that our population has nearly doubled since 1974. So there are almost twice as many people alive on the planet as there were in 1974. So think about that, right? How long ago was that? How many years ago is that? How many years ago is 1974? Calculate it in your head. See if you can do it. This little line right here, those are the planets. Those are the planets. You can see that there's the sun, the big one. There's Mercury, Venus. Earth is jumped up a bit just to indicate that we are here. You know what I mean? And then you've got the longer lines to represent the gas giants: Saturn, Jupiter, Uranus, and Neptune. They also included Pluto because back in these days, Pluto was still considered a planet. And then this part down here, that's just a picture of the radio telescope. Incidentally, this is what the telescope looks like. Check this out. Yeah, so it's a gigantic crater dug out of the ground, and that's basically a giant parabolic satellite dish. So think about any satellite dish you're used to seeing, right? The stuff comes in, the information comes in, bounces off of the bowl at the bottom, and reflects up to that focus, and we can interpret the signals that we get. And we can also reverse that process by projecting down to the disk, and it'll project out into space. So it's just kind of cool, right? I don't know, this type of stuff's cool. Um, all right, and then so this is funny because down here they say, oh, this is one way you could encode it. If you factored it the other way and like wrote them that way, then this is what you would get. But you can see even with this breakdown that it's not totally random. It's not totally chaotic. There's a pattern there. So even if the aliens factored it like this as 23 rows and 73 columns instead, they would be able to tell something is there, right? And then, oh yeah, apparently there was actually a hoax back in 2001. There was an answer, and this was the picture they sent back. You can see like there's a little red alien over here, and they like made a crop circle and that kind of thing. It's yeah, it's silly, right? There you go. Hampshire, UK. Anyway, so this is just one of those interesting things that shows how primes and composites and factoring and multiplication, these are universal concepts that even aliens can understand, and it allows us to communicate with them, right? Remember, it's a language. Math is a language that we use to describe ideas. The ideas exist outside of the language. Anyway, if you want to read more about it, go for it. It's really, really interesting. And read more about Carl Sagan and Frank Drake if you'd like too. All right, but we need to keep going. So this slide just has a bunch of those things that we just talked about on it: solar system, the telescope itself, et cetera, et cetera. But now this is an interesting question. Okay, so let's read this question that we might ask one of our students. Suppose you have n tiles. Now, if n equals 12, in how many ways can you rearrange the tiles so that each row has the same number of tiles? Okay, so now this is interesting, and I'm going to break out my linking cubes for this. Oh, I dropped something. Oh, that's just my Okay, it's not so bad. Whew. Ah, just my snack. Okay, so what was I saying? Oh, I'm going to use these linking cubes to indicate what's going on here. And this is exactly what you would do with your students in your classroom. Okay, I'm just going to put all these cubes together first. There's 12 of them here, so this will work perfectly. All right, 1 second here. Still stick these together. All right, so here's the idea. And I'm going to cut to the camera in just a second so I can kind of show you what's going on. But here are 12 linking cubes. So pretend these are the tiles in this question. And the question says, how many ways can I arrange these tiles so that each row would have the same number of tiles? Let's try it out, shall we? 1 second here. Let me go to the camera so that we can see things a little better. Okay, so one way I could do it is just like this. This is a 1 by 12 rectangle, right? It's it's 1 unit tall by 12 units long. There we go. Now, how else could I make it so that each row has the same number? Well, here's a natural one, like that. There's another way of doing it. Now I've got 2 rows, but each row is 6 long. Is there another way I can do it? Can you see one? That's right. Take this, and we can actually do this. We could try doing something like this. This should look familiar, right? Should be a rectangle. Pretend it's a perfect rectangle. So now we've got a height of 4 and a width of 3. Isn't that interesting? That's exactly what we were talking about before, right? Those are the factors of 12. Those are the factors of 12. 1, 12, 2, 6, 3, and 4. That's it, right? And this is how you would visually represent that. This is how you would visually represent that. So once again, you've got, what is it? Here we go. 2 times 6, that's equal to 12. We saw 3 times 4. Now we've also got 1 times 12. So there's a bunch of different ways to arrange these things, right? Now, let's try this again with a different number. What about the number 11? Let's look at the number 11 and ask ourselves the exact same question. How many ways could we make the rows? So I'm going to take one of these off. Here we go. Now I've got 11 of these things. 11 of these things. All right, now let's see how I could arrange the rows. How about like this? Here we go. Oh, wait, that doesn't work. There's a hole right here. That doesn't work. Bummer. Okay, maybe I took too many. Maybe if I do the other one like that. Oh, there's still this other little gap here. How else could I? Maybe like this? No. Maybe, wait a minute, like this? No, there's still a gap right here. What's going on? What do you think's going on? What is it about the number 11? That's right, it's prime. 11 is a prime number. And remember what it means to be a prime number. It means it's only got 2 factors. It means you can only write it as 1 times that length, 1 times itself. And that's exactly what's going on here, right? Because remember, multiplication can always be represented as an area, So here, the only way we can represent this as a rectangular area is 1 times 11, because that's a prime number. This is exactly how you explain prime numbers to children. That's what it means. Because then they can take that model, that area model, that visualization, and carry it with them forevermore. This is what a prime number looks like. It looks just like this, because I can't make any nice rectangles other than this one, other than 1 times that number. And that's it. That's what it means to be prime. Okay, so that's a really, really good edifying example, and I encourage you to play around with it yourself. Okay, so now let's look at some definitions. These are definitions that you need to know, that you need to memorize. You need to be very comfortable with these. So, and also one thing I'll say here is that in this chapter, we're going to use more advanced, notation. So for example, I'm going to say that's m times n. I'm not going to write the times all the time because this is a more rigorous chapter. All right, so if m times n equals p, m and n are called factors of p. That's what we had talked about before. P is called a multiple of m and n. So in other words, if I take m and multiply it, or I should say add it, n times, then I'll get to p. That means p is a multiple of m, and p is a multiple of n. Um, if mn equals p and m is not 0, then m is called a divisor of p. And we actually talked about this back in, what chapter was it? I think it was chapter 3. I can't remember if it was chapter 3 or 4, but we talked about divisors briefly and we talked about factors briefly. This is where it's going to become critically important to know what a divisor is. Um, so if m is a divisor of p, we say that p is divisible by m. Okay, so let me highlight all that here. That's the idea. So in other words, if p is a product of m and n, and those are non-zero numbers, then each one of them is a divisor of p, and we say that p is divisible by each of them. And we're going to get lots of practice with these terms in a minute here. Okay, this is where you're going to get some new notation. So you might have never seen this notation before, but let's let a and b be whole numbers. Now we say that b divides a. B divides A, and we write it like this, if and only if there's a unique whole number Q such that A equals B times Q. Got what? What? Say it. Say that again? Yeah, exactly. This is why with definitions you have to read them and reread them and say them out loud and try to rephrase them, write them in your own language, that kind of thing. Let me say it again here. So I like to say things in my own words. I think it makes it clearer for me. We say that B divides A if A is equal to B times Q. That's what it means. But what does this mean right here? Well, this means that this means that B is a divisor of P, or sorry, B is a divisor of A, and Q is a divisor of A. And this is the relationship. We say that B divides A if we can write A as a multiple of B. That's what we're trying to say. And I can explain that more and more and more in the collaboration meetings. I'm going to say it some more right now too. But here's some vocabulary that you need to be very comfortable with. So I'm just going to let you pause here, pause the lecture, read these things for a minute, read them out loud to yourself, and think about it. Okay, and now that you've thought about it, say some of these things out loud, because I'll tell you what, these things over here, that entire list, those are all saying the exact same thing. Those say the exact same thing in 5 different ways. So think about it and then talk out loud. Say these things out loud and see if you can make sense of them. Okay, let's come back now. So yeah, like I was emphasizing, this list over here, those all mean the same thing. So hopefully you said these out loud. But if I say that A is divisible by B, then what I'm saying is that B is a divisor of A. I'm also saying that B divides A, right? If A is divisible by B, then B divides A. But if A is divisible by B, then B must also be a factor of A. And if B is a factor of A, then B divides A. And if B divides A, then A is a multiple of B. And if A is a multiple of B, then B is a divisor of A, and A is divisible by B. These are all the same thing. These are all the same thing being said in 5 different ways. But depending on the context of the problem, you might want to focus on the fact that something is a factor, or you might want to focus on the fact that something is dividing something else. So we need this terminology and we need this vocabulary to help us talk about the relationships that we're going to explore. The other thing is over here on the right, that symbol, this little vertical bar symbol, literally translates to the word divides. So if you see something like this, it literally means 3 divides 12. Literally, direct translation, literally. Similarly, if you see this symbol, the little line with a slash through it, that means does not divide. Does not divide. The same way that you would say, oh, if something is equal, I would say now they're not equal, right? Exactly the same symbol, except now we're saying, hey, does 7 divide 12? No, 7 does not divide 12. 7 does not divide 12. So this is new notation that you might not have seen before, but you do need to be comfortable with it. Just remember the bar directly translates to the word divides. That's what the bar means. Okay. So the reason that I was focusing on this and the reason that I was saying that you need to memorize these things and be comfortable is because of this. We have to be able to attend to precision at this level. This is from the book. Mathematically proficient students try to communicate precisely. They're careful to use vocabulary that's appropriate to the situation. The vocabulary of factors, multiples, divisors, products, and so forth can be very challenging. It was challenging for me. It's going to be challenging for you. It'll be challenging to your students when you're teaching them, right? But it's critical to mathematical communication because we have to be on the same page. We have to know what we're talking about. And so we spend time ensuring that that's possible. Um, and also, these words extend through the curriculum and beyond. Whenever you hear the word divisible or divides or factor, it means the same thing. Like it literally means the same thing out there in the real world, right? It means the same thing. So you want to be able to make sense of these terms. Okay, so this is one of my favorite experiments here. I love this one. It's critical that students understand the difference between factors and terms. Okay, factors are defined as above, right? What is a factor? We saw that. Here it is. Boom. Here's the definition of factor right here. There we go. That's the definition of factor. So we know what factors are. Terms Terms are expressions that are separated by plus and minus. That's the critical thing. So another thing you'll notice after you teach for a while, a lot of the times when students are struggling with computations, it's because they don't understand the difference between factors and terms. So here's one of my favorite examples, and this is going to be one of those Dora moments, right? So let me get this ready here, and we're going to practice for a minute. Okay. Let me write an expression here. Which expression do I want to use this time? Well, let's start with something easy. Let's do this. Let's write two. Do I want to do it that way? Okay, let's do this. Actually, a little more advanced example would be easier, I think. Funny enough. How about this? I'm going to write x squared plus 2x plus, do I want to do that one? Hold on a minute. Let me think about this for a minute. I want to pick something that's going to look nice here. So let's do x squared minus x plus 2. Minus x plus 2. Okay, I think that'll work. All right, so here's my question to you. How many terms are in that expression? Oh, sorry. How many terms are in that expression? How many terms? Think about it for a minute. How many terms are in that expression? Okay, now talk out loud. How many do you think are there? Talk with your group. What do they say? How many terms are there in that expression? Okay, let's do it together. Well, in this expression, there are 3 terms. There are 3 terms, and they're right here. Here's 1, here's 2, here's 3. There are 3 terms, all right? Now, the second question is this. How many factors are there? How many factors are in this expression? How many factors do you see? Think, talk. It's an interesting question. Some people might think there are 4 or 2 or 3 even. There's only one factor here. There is one factor, and the one factor is the entire thing. There's only one factor. So there's one factor. Okay, now I'm sure some of you were already thinking about this, and hopefully I picked the right problem. But this is one of those numbers that oh wait, is that going to work? I don't know. This one won't work. Hmm. Let's try a different one. I think I got the negative signs wrong. But you can see that there's three terms and one factor. Let me play around with this. I was trying to do this in my head. I should have written it down, right? Let's see. I think this should be. There we go. Yeah, okay. How about this one? So let's same question, right? How many terms and how many factors are here? So go ahead and take a minute and think about it and talk. All right. Okay. So how many terms and how many factors? So just like before, there are three terms, but how many factors are there? Some of you might be tempted to say two, but there's just one. There's one factor there. There's only one factor there. What you're doing is you're doing a computation. If you're thinking that there's more than one factor, you're doing a computation. What's that computation called that you're doing? Factoring. That's what factoring is. Factoring turns expressions that have multiple terms into expressions that have fewer terms. So let's go ahead and factor this. You don't need to be able to do this for this class. You don't need to be able to factor trinomials, but some of you probably saw that this was this. X minus 2 times x plus 1. You can FOIL it out, and you'll get this right here. Okay, so now that we've done this, this is the really, really cool part. All right, so looking at just the left-hand side here, I'm going to ask the exact same question. How many terms are in this expression, and how many factors are in this expression? So just take a moment and think about it for a minute. What do you think? All right, now talk out loud. What do you think? Four, three, two, one. What do you think? What do you think? Okay, so the reason I love this is because there are two factors. So I think everybody realized that there are two factors, and you can see the two factors, right? The two factors are right here. Here's one, and here's two. There's two factors in that expression. Now, how many terms are there in this expression? You might be tempted to say four, but the answer is one. There's one term. There's one term, and there it is. It's the whole thing. That's the one term. Remember, what is a term? Terms are separated by plus and minus. This thing right here that I circled, there's no pluses and minus separating that thing, right? This is an object in and of itself. And there's only one object there. It's one term. There's only one term. So the cool thing is this, the process of factoring, how we went from here to here, is a process that turns something with a lot of terms in it into something with one term, but a whole bunch of factors. And that's why we like factoring, because if you can represent something as a product of a whole bunch of things, you can do other stuff with it. So that's something to keep in mind. There's one term there. Now, if I start focusing on individual pieces, then that question changes, right? If I say like, oh, how many factors are in this term? There's one factor there. How many terms are in there? There's two terms. There's two terms. There's this one and this one. So it depends on what you're looking at, right? So it's very, very important to understand the difference between factors and terms. A lot of times if people have issues canceling or reducing fractions, it's because they don't understand the difference between factors and terms. And I think we'll talk about that later. But anyway, oh, that's it. That's it. Okay, so let's take a look at activity 11A, and then we'll call it a day. Come on, what are you looking at? Oh yeah, this is one of my favorite activities. Okay, so this is an involved activity. There's not a ton of work, but there's a lot of exploration you have to do. This is a great one to do with your group. But it says this. In a school, there are 100 closed lockers lining a hallway. Suppose 100 students walk down the hall in single file. The first student opens every locker, okay? Then the second student comes along and changes the style of every other locker, right? Comes along, yeah, closes every second locker, beginning with locker number 2. So 2, 4, 6, 8. And then the third student comes by, and the third student changes every third locker. So the third locker, the sixth locker, the ninth, and so on and so on. And every student proceeds that way, all right, until the 100th student is only going to change the position of the 100th locker. That student's going to skip all the first 99 and only touch the 100th locker. So my questions are these. At the end, how many times did locker 9 get changed? How many times did locker 12 get changed? At the end, which lockers exactly are open? And when I say exactly, I mean give me a list of the lockers that you know are open at the end. It's not going to be super long, but which lockers exactly are open after all 100 students go through? And then lastly, why are they open? Why are they open? You might be able to figure out. I don't recommend brute force calculating it, but you might be able to figure out, and that's what you're trying to answer here. What's the pattern that you see? Um, some suggestions I can give you are to, you can draw a table. You can draw a table, but the table is not as hard as you might think. What I would do is I would write down the first maybe, I'd say maybe the first 30 numbers. Just write down the numbers like 1 through 30 and just go through and see what would happen if each student changed the lockers. So like, on a piece of paper, you can say like 1, 2, 3, 4, 5, 6, 7. Go all the way to 30. And then one thing you can do is you can just say if it's open or closed. So the first student goes by and opens every locker. So they all start out open, right? And the second student is going to come and close every second locker. So they'll close 2, 4, 6, dot, 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 and 30. And the third student's going to come by and touch every third locker, but leave everything else alone. So they're going to come by and close that locker, and they're going to open locker 6, and so on and so on. And if you do that for the first 30 students, you should be able to see the pattern. But try to figure out what the pattern is and tell me why they're open. Why are they open? Okay, so that's it for today. Like I said, this is kind of a long chapter, but this particular section of the chapter is not that long. The second one, the one that we're going to do next, that's the longest one. That's the one where we have to do all of the divisibility tests. So the divisibility test for 2, 3, 4, 5, 6, 8, 9, 10, and 12, and more actually. So the next lecture is probably going to be a little bit long, and it's also technical if I remember correctly. Anyway, as always, if you've got questions, please ask, and please ask at the collaboration meetings, and I'll see y'all next time.